Good afternoon. You can pass your homework to the front if you haven't done so. Tanisha is here to pick up the homework. Okay, today we're going to start looking at n-squared charts. But before we do that, let me give you back your quiz on causal loop modeling. So we had an in-class exercise, and most of you did very well. So we were supposed to create a causal loop model for an ideal hotel, and we'll go through some, I'll give you some comments. No, Young, Suncow, Avis, Aditya, John Paul, Eric, Salazar, Topper, John, Derek, James, Kathikeyan, Duraisami, Anand, Madeline, Naisha, How. Okay, for the DL students, make sure you email me your causal loop model if you haven't done so. So causal loop models are great for soliciting information, especially if you are doing systems thinking studies in organizations. You gather your team, and then you can go through this process. And in this particular ideal case, we were trying to find ways basically to improve service quality. Okay? And so we have to provide our notation. That's the first thing for our causal loop model. So if you did not provide notation, you lost a point. And then if you did not answer this question, you lost 2 points. Then if you missed out something else, I decided to give everybody credit there. Since it was your first time, you have more practice later. So for the ideal causal loop model that we looked at, we may end up having something like this. Okay? So remember, this open arrowhead is for reinforcement, and the solid one is for opposing tendency. And here's an example of a causal loop model for this situation. Basically, if we look at this, and most of you had this correct, the only difference was right here between business revenue and cost efficiency. So the notion we can actually capture from this is that improving this service quality can increase customer satisfaction. But that doesn't come for free, right? Because we have to incur costs associated with equipment, staff, based on whatever you listed here. So if you improve the quality of service, then that can increase customer satisfaction. Customer satisfaction can result in more business. You have a question? Mm-hmm. Yeah, I'm getting there in a minute. Let's go through this. The question is this cost efficiency and business revenue can this go both ways? Okay. Right now we are looking at it this way. We look at the quality of service. If we improve that, then we can actually provide better customer satisfaction. Then that can increase business revenue. And of course, that can give us even, we can make even more profit. And some of the profit we can actually put back into the business. For example, we can put it back to pay staff better or hire more staff, put it back in the equipment. But also because we have more money here, that money can be used to, in essence, help improve the cost efficiency. Cost efficiency has to do with you don't want to spend too much money on staff, but you want to still maintain a high level of service to your customers. So you want to basically reduce your costs, but still maintain high quality standards. And so the equipment and staff can actually lead to more costs. And most of you made that observation. What would be the impact of costs on cost efficiency? This is going to oppose. Everybody see that? So one thing we notice is that we have an ever-ending cycle of trying to maintain improvement. And also another observation that was just made is that, for example, if you look at maintenance, here we are showing that maintenance, if you improve it, it's going to reinforce service quality, right? But at the same time, it can go the opposite way. If you don't improve maintenance, what's going to happen to this quality of service? It can go the opposite way, okay? And so with causal loop modeling, we can see that in many cases we can go either way. And so it is important to have all the contributing factors included in your causal loop model. In this case, for example, we see that we have this cycle of continuous improvement. That's what we need. So the arrows are basically indicating that we need to have reinforcement, but it can also work in the opposite way. For example, if we reduce the service quality, what's going to happen? It's going to spin the opposite way, right? So in this case, we see that there is no external reference to feedback because, again, this is an ideal causal loop model. It's basically saying that the only way to guarantee this high level of service is to have something that's going to provide us with continuous improvement. Also, another point we should make here is that when you look at all the factors, if you don't do well in any one of them, that may affect the entire quality of service. For example, based on the comments that you listed on your experiences regarding your hotel stay, some of you wrote poor laundry, right? You may have everything else in place, everything else is great, but just one thing is not good. Some of you said bad food. Then for you, the service quality is not good enough, right? So the causal loop model is basically suggesting that to have continuous, to have a high level of service quality, it means you have to have continuous improvement, and you have to make sure that all these factors that you listed are actually taken into account. Also, you have to put money back into the business in order to do that. But we have to keep in mind that this particular causal loop model is more like out of context, because we are not talking about other issues associated with hotel business. So just keep that in mind. So we need something else to provide this, some kind of feedback. So the causal loop model expresses openly and very clearly the thoughts and ideas of the modelers or people creating this, the causal loop model. It allows for discussion. Okay, so once you build this, it's going to bring up issues. You're going to start asking questions. What about the opposite? So it enables dialogue, and also it allows for correction and further improvement. So once you create a causal loop model, that's not the end. You have to, you may have to go through several iterations before you come up with a, before you capture the situation. And also it is useful for representing behavior of nonlinear dynamical systems. Remember, we started with the idea that the linear way of thinking is not good enough. The world, for the most part, is nonlinear, so we have to think along those lines. So when we have issues associated with systems engineering, we have to look at the big picture. And causal loop modeling allows for us to capture or gather information about an issue, especially with complex systems. Okay? So you're going to use this causal loop modeling later on in your project, early on, to try to understand whatever complex system you'll be looking at. There'll be many issues associated with the customer needs. You're going to try to come up with system requirements. And so causal loop modeling is going to allow you to have a way to look at different aspects of the system. The other tool that is used in systems thinking is known as an n-squared chart. And this is very popular. It is very simple. It's a table with n rows and n columns. That's why it's called n-squared. It's n by n. And what it does is it allows you to record entities and the relationships between the entities, the relationships or the interchanges between entities. Usually we put the entities in the leading diagonal, and then we place the relationships in the other cells. And let me give an example of an n-squared chart. Here is an example that has these entities. Professor, we have teaching assistant, we have a student, we have assignment. So we may want to try to understand the relationships and the interchanges among these entities. Maybe this is for an educational system. So for the n-squared chart, the leading diagonal is going to contain the entities of interest, and then the inflows refers to what each entity is going to receive. The outflows refers to what each entity is going to give, the output from the entity. So the outflow is going to be written along the horizontal, like this. So if we think of professor as an entity of interest, then we can write in these cells the output from professor going to the corresponding entity. And in the same way, we can write the inflows for the professor. It could be the exchange or interchange of information. For example, assignment to professor, students to professor, then TA to professor, that's going to go in here. For the students, it's going to go in here, and so on. So this way is going to be the outflows, and then this way is going to be the inflows. Okay? This is going to be very, very useful early on in your system analysis when you're trying to understand a complex system to be designed or an existing system, and you're trying to figure out the relationships or interchanges between the different entities of the system. Okay? So let's go through this as an example. Suppose we are trying to understand or design a system. It's going to be part of an educational system. So we have entities shown here, and we're trying to see the interchanges between the entities. So let's start with professor. So what do professors do in relation to teaching assistants? What can the professor give to the teaching assistant, in other words? So you can speak up. Comment? Speak up, please. I didn't get what you said. Oh, command. So you can give a command to the teaching assistant? Well, you may. You may do that. What else besides giving commands? I usually don't give commands. Teaching assistants are students just like you. We don't give commands to students. Remember, it's an open loop type system. You can ask the student to do stuff. They don't have to do it. Okay? Yeah, we give advice, and we are sometimes called advisors. I advise 6 PhD students, so I give advice. They don't have to listen to my advice. So advice is one of the things that the professor can give. Pay? Yeah, you can pay for the teaching assistant monthly stipend. We support students. I support students as well. In terms of teaching, I can give assignments or grading assignments to the TA. Okay, so I can ask the TA to grade the homework. Then I can spend more time doing something else. How about the TA? What can the TA give back to the professor? If I give the TA grading assignments, they can give me back graded assignments. What else? Correcting the homeworks. Yeah, they can collect the homework. They can provide feedback, and so on. They can give advice too. You know. Yes, they can do that. So we can list a whole bunch of stuff that the TA can do. How about the professor and the student? The professor can give knowledge or instruction. This is, again, can teach. We're talking about teaching. And what does the student give back in return? The student can give attention, the student can ask questions, the student can give feedback, and so on. The professor can give homework, can give assignments, the student can give back graded completed assignments. Okay. Then let's move on to the next one. The professor can prepare assignments or write tests. And what happened to the assignment in relation to the professor? Okay, so that can provide feedback. What kind of feedback? Performance, student performance. Okay, so we have the outflow and then we have the inflow. In the vertical cells and then the horizontal cells, we have the outflow. Okay, how about let's move on to the next entity, the TA. The TA and student. What can the TA give to the student?
Guidance.
They can give guidance. They can give graded assignments or homework. What else? They can give reference books. We have reference books. If you need to check out a textbook, you can go to the TA. How about the information coming back from the student to the TA? The student can ask questions, right? The student can ask the TA questions. The students can provide the TA feedback, and so on. Okay, then we move on to the next cell, the TA and assignment. TA and assignment. They may add questions or they may not do anything. So since most of you are quiet, I'll leave it blank. It's okay to leave it blank. You don't have to put stuff there if it's not there in the actual system or the system to be designed. So we'll leave this one blank. And assignment back to the TA. We can leave this one blank too. Anything that the assignment can provide to the TA? Yeah, if you feel that strongly there should be something here, then we can put something here. Yang, you want to say something? No? You don't want to put anything here? Okay. He said that the assignment can give the TA stress. Well, that's a good one, right? Okay, how about the student and the assignment? What does the student do to the assignment? They have to do it, so they have to complete the assignment, right? Okay. They don't have to, they can leave it. How about the assignment to the student? What does the assignment provide to you? Grades. So the assignment can provide learning. Okay, assignments are designed to reinforce learning. They can also provide a grade or contribute towards your grade. Assignments are meant to provide knowledge. You may learn something from the assignment. Okay, so this is a very simple example of an n-squared chart. So everybody doing fine? Okay, so this is how we just constructed one. Again, in an industrial setting, you'll be doing this in teams. Okay, it looks very simple here because I have very simple entities I'm looking at. Everybody can relate to this. And that's why I'm using this as an example. So I'll show another example in a few slides. But let's look at this in more detail. N-squared charts allow an overview of a system. So if you have a complex system, one way to try to get a good picture of what's going on is to construct an n-squared chart. Here we have this example of an n-squared chart which shows 3 systems that interact. Okay? Just looking at the n-squared chart, we can actually see that system 1 and system 2 actually do interact, and we are showing this using these digraphs. So we can put digraphs, and this looks like a causal loop model, right? You can actually see that there is reinforcement going on between system 1 and system 2. Similarly, between system 2 and system 3, there is some interchange going on there. Okay? So remember we talked about interfaces and interactions before? So for this system, we can see that there is an interface or a connection with system 2. So this is an interface, okay? And typically interfaces tend to occur in pairs. Okay, so you have one system, or could be a subsystem. It may be connected to another system, so you have an interface. And those can form these causal loops. Yes, you can, yeah. So the question is, can you create an n-squared chart with interactions between different levels of the hierarchy? Yes, you can. Okay. So as you see in a minute, constructing n-squared chart becomes a little bit complicated because you may have a complex system and you may have to create n-squared charts for different layers. And then you can show the interchanges between the layers. Okay? Okay, so n-squared charts is usually they will contain these loops. One thing I forgot to mention with causal loop models is that the causal loop model and the n-squared chart actually provide a way to capture dynamic behavior. Okay, so we are looking at a static picture, but we can actually simulate the behavior of a system just based on a causal loop model or an n-squared chart. Okay, so in this particular example, we looked at the interfaces between systems. Then we can see that these interfaces actually allow for the systems to interact. Okay, and in this case, we have 6 interface cells. So 1, 2, 3, 4, 5, 6. Those can be used for interfacing these systems. But we only see that system 1 and 2, they are connected. They have an interface, 1 and 6. And then we have an interface between 2 and 3. So this interface and this interface cell. Okay. So communication between 1 and 3, in this case, may be happening through system 2, right? System 1 can pass information to System 2. System 2 can then pass information to System 3. In another case, you may have direct connection from System 1 to System 3, or from System 3 to System 1. Okay? Now, when you have an n-squared chart, sometimes you may be looking at a complex system, and so you may have actually subsystems involved. Again, this is talking about different layers of the hierarchy. And so it is very important to remember that an n-squared chart has to be in a given context. Remember we talked about the system environment. Sometimes we want to represent the system environment as well in an n-squared chart, and we can do that. So in that case, we can surround the n-squared chart with another layer to basically show the whole system. Okay, so yeah, here's an example. So we can have our system of interest could be system. This system consisting of A, B, and C. Okay, that could be something that we can actually analyze in more detail, as I'm going to show in a few slides. But we may also be interested in trying to show how this system is going to interact with other systems in its environment. So here we can have this system X, and we can have system Y in this environment. So we can construct this n-squared chart, and then we can actually put this overlay as the environment and also depict the specific systems involved. For example, ABC can be a car. So we have an n-squared chart for a car, and this car has 3 subsystems. A is the chassis, and then B is transmission. C could be, for example, suspension. Okay? So this is how we are capturing this car. But this car has to interact with other systems in its environment. So X, for example, could be a person, the driver. Okay? And then we can also add Y. Y could be maybe some vehicle test system. Okay? Maybe you have to test your vehicle emissions. So this gives you a pictorial representation of this system in a particular system environment, just using an n-squared chart. Okay, so that's context. So we looked at interface, interaction, and then context. The other thing we need to look at is patterns. Remember from the systems constructs, we looked at patterns as well. The pattern actually is something that you can notice. So once you construct your n-squared chart, you can actually see something about the n-squared chart. For example, in this particular n-squared chart, we can see that we have system A and B. They seem to be co-located over here. So this can be what is known as a functionally bound block, meaning that system A and B may be performing a particular function together. And so that's why they have these interchanges between them. Okay? So you can see here there is an interchange and interchange. Okay? Or an interface. Okay? This means there is you can think of it as having a connection. Okay? What else do we notice here? We see that system C is in between system A, B, and the rest of the systems over here. So we can see these patterns in this picture, right? So in summary, an n-squared chart can be a valuable tool for amassing a lot of information about a complex system or project. The rows and columns can be interchanged so as to create different patterns. For example, if I move, I can move system A from this cell and I can put it here, and I can move G and put it here, right? I can do that. I can interchange all these entities. All I need to do is maintain the interfaces which are going to allow for interactions. So I can come up with a different pattern, okay? And again, I'm going to talk more about this a little bit later. But right now, what I want to say is that the n-squared chart can reveal some typical patterns. For example, you can see these functionally bound blocks. You can also see some mutual interfaces. Basically, what this picture is telling me, for example, is that if I'm going to design this system of systems, then maybe I would like A and B to be close. A and B should be adjacent because there will be a lot of communication there. D, E, F, and G, maybe they should also be put together somewhere, right? And what else do I see about, what can you say about C? C is by itself, it's in between, right? Suppose this is a real system of systems. What happens if I take away system C? Okay, if system C breaks down, what's going to happen? There will be no interaction between system A, B, and system D, E, F, and G, right? So if I see that this is going to be my design, then I have to be careful how I design system C. In case system C fails, maybe I need to have a backup, right? So this basically, I'm just looking at the n-squared chart. It means that this may be a critical system because it's allowing for interaction between two different parts of the entire system of systems. So that information is revealed to me just by looking at the n-squared chart. Okay, so interface patterns. The next concept is the concept of encapsulation and elaboration. As the name suggests, encapsulation is basically trying to encompass or contain entities. And the opposite of that is elaboration, trying to expand. Okay, so encapsulation is a system concept. We use this term a lot. So let me give an illustration of what this means. The functionally bound block, for example, this one here, which comprises system D, E, F, and G, can be encapsulated. Meaning that instead of looking at it in detail like this, we can actually encapsulate it and look at it as just one system. And I can write it like this or draw it like this. So I'll call this one D, system D, E, F, G. I'm not showing the details because I'm trying to encapsulate it. Okay, so when I say system D, E, F, G, I mean this system here. Okay, so I can perform this encapsulation. So basically, it's more like you compress it, you hide the details. And elaboration is the opposite. if you give me a system like this, then I want to see the details of the system, then I can do an elaboration, basically going back. Okay, so I can expand this back, and that gives me an elaboration. So of the entire system of systems, we can encapsulate this and create another n-squared chart, which can look like this. So we have system C. So C is going to be here. I can encapsulate A and B, and I'll call this AB. I can put it right here. So encapsulation means I move from this n-squared chart to this one, and then I can move back here if I do elaboration. Okay, but we still have to maintain the communication or the interfaces that we need. So there's an interface there, there's an interface there. So these are interfacing cells. We have to maintain those. Okay, so this idea of encapsulation allows us to basically hide details. So we can create a series of n-squared charts just for one system at different levels. And using this idea of encapsulation and elaboration allows us to actually do this. Okay? Why do we have to do the encapsulation? It allows for reducing the perceived complexity of the system, as well as the entropy. You know, it looks like it's very disorganized. So this one looks much simpler, right? So that's encapsulation and elaboration. These concepts are used in, we may talk about this later when we start looking at systems modeling in the next few weeks. Any questions, by the way, so far? Everybody doing okay? All right, here is a more realistic n-squared chart. So let me go through this just to illustrate what's going on. This one is for an airspace management system, which is ASM. Okay, so basically we are looking at controlling aircraft. So we have this controlling airspace system, and we also have in terms of controlling aircraft, once the aircraft takes off, then it's controlled by this this system here. Okay, when the aircraft is approaching a given airport, it has to be controlled by another system which deals with approaching or aircraft that is taking off. Okay, once the aircraft lands, the control is given to another system, which is in this case represented as controlling ground movements of aircraft at an airport. And once the aircraft is heading towards the gate and gets to the gate, some other system takes over, and this is ground marshalling of the aircraft. Okay, so here we have these entities. Let's start with this one, aircraft general flying. So an aircraft is flying. So it's going to send information. So remember, the outflow is going to go this way, and then we're going to have the inflow this way. So this aircraft can send its status, its position, its vector, and other information to controlling airspace system. Okay, And then this system can provide the aircraft with feedback such as the data, the warnings, the rules, basically communicate back with the pilot. Okay, so we see that. And there's nothing else here. There's no other information that's being sent from the aircraft for general flying. And the only feedback we get is coming from the controlling airspace system. Then we have an aircraft approaching an airfield, which is the next entity in the n-squared chart. Then we see that for this approaching aircraft, actually it has to send information to controlling approach. Okay. Remember we looked at controlling airspace. This one, once the aircraft is approaching an airport, then it hands over control. So they basically transfer the control of an aircraft once it reaches a given zone or given area. So the United States is divided into different areas. Each area has its own, control for the airspace. And once the aircraft approaches the airport, then the controlling airspace hands over. So there's a handover to the controlling approach system, which gives feedback saying it is taking over. So we have this taking place. And so the approaching aircraft is going to provide its information to the controlling approach takeoff, like status, the speed, and so on. Then the controlling approach is going to provide the data about the airfield, the airport, the corrective actions as well to the approaching aircraft. Okay, and then also there's this information which is going to come from this one. So let's move on to the next one. This is now landing. The aircraft is about to land. Then it still has to provide the status, the aircraft position to this controlling approach. Also, taking off aircraft has to do the same thing, provide this information. Okay. Then let's move on to this one, controlling ground movements. Once the aircraft lands, then this system hands over control. So it hands over control to the ground movement control system. And this one gives feedback that it's taking over. And then the controlling ground movements, usually air traffic controls at the tower, they will tell the plane what to do. So they'll basically, this is now aircraft taxiing. Okay, so this is where we are now. So the airplane is taxiing either to the runway or from the runway to the gate. And so the controlling or GMC controlling ground movement is going to give directions, signals, destination. They may tell the plane to stop and wait, and so on. And then the aircraft is going to provide its status, its position, and where it's going, and so on. Once the aircraft gets to the gate, then it's taken over by this ground marshalling. Okay, so there is cooperation between aircraft taxiing and the ground marshalling, and they give instructions back to the aircraft. So we can see that the n-squared chart provides a mass of information, but in addition, we can see that there's this idea of time being revealed. Even though this is just a static image, we can see that there's dynamism involved here. And so we can actually build a simulation of this system, of systems, given this n-squared chart, if we understand what each of these entities actually, what functions they're going to perform, and so on. Okay? So, and that's just the nature of n-squared charts. Questions on n-squared charts? One more comment. about n-squared charts is that actually programs can be devised to rearrange. Remember we talked about you can create one like this because you don't know how to, the best way to arrange the entities in the leading diagonal. So based on the order, you're going to come up with a particular n-squared chart which may look like this. Right? In this case, this is just showing the connections or interchanges between systems. Then when you change the order, you can find a way to actually create nice patterns like this one. If you remember in your facilities planning, we do something similar when we are trying to design layouts. Okay? So to design layouts, we look at departments that have to be close and departments that have to be far apart. So we can look at the adjacency score, which is similar to this, right? You have an n-squared chart like this. Look at this arrangement. You can have a score. Basically, it's an adjacency score. Here it's 86. You want to minimize that. Then you rearrange. Here you have A, B, C, D, E, F, G, H, I. You're just rearranging the entities, and you come up with a different score. And this can provide you with something like this. And now you can see at the patterns now. What does this tell us? It tells us that we actually have maybe three systems or three subsystems. And you can see that C basically connects system AB and system D, E, F. So you can see this one here. Also, you can see G is more like connecting D, E, F, and HI. Okay? And so we can use this information in our system design. Okay, any further questions? Okay, I think I'm going to stop here. I typically like to stop here because there's more stuff we need to cover. So we need some modeling background and so on. In terms of systems thinking, at least we have an overview of systems thinking. But systems thinking is a discipline on its own, and there's a lot of information about it. I don't have time to go through systems thinking modeling methods, but I want you to be aware. So I provided a reading assignment for the next homework, and I would like you to read on two systems thinking modeling methods. One of them is called the soft systems thinking approach or the rigorous soft method. The other one is called the generic reference model. I want you to read this, and I think I asked a few questions at the end just to make sure you read it. Okay? Then you can answer those questions. But for the most part, it's a reading assignment to help you be aware that systems thinking is actually a practice that people use in industry. Okay? So next, we're going to do an exercise, in-class exercise, to give you an opportunity to create n-squared charts. This is going to be an individual exercise. Okay, so this won't be a team exercise. For the distance learning students, if you go in the lectures folder, there's a PDF which says quiz number 4, and that's what you need. For the in-class students, I'm going to pass this to you. That's what you're going to need to use. So the question is to construct an n-squared chart for the case shown here. Okay, so remember we looked at this before. We are trying to control a radio-controlled air vehicle. Over here, we are basically looking at finding or moving the aileron. And so we can understand this system better by constructing an n-squared chart. And I selected entities for the n-squared chart, which I think are important to capture what's going on in the system. And I want you to basically fill in the blanks. Don't forget to write your name. I want you to think about what's going on in the system and make sure that you carefully think about each cell. Each cell needs to have specific information. If you leave it empty and there's something that needs to go there, then you lose a point. If you put something that's not supposed to be there, you lose a point. So I want you to think carefully about each individual cell. Okay, everybody has a handout. Okay, so individual exercise. We have 10 minutes to do this. I'll go ahead and stop the recording since this is going to be the end of today's lecture, and I should be able to post slides for the next week's lectures by the weekend. Okay.